So it is my pleasure to welcome Mr. Saptarshi Saha, who is currently a PhD researcher, PhD scholar at Department of Physical Sciences here at IISER Kolkata. And his research interests mainly include quantum information and quantum foundation research. And today he'll be giving his talk on prethermalization and dissipative dipolar system. So Mr. Saptarshi Saha, the stage is yours. Thank you.
Yeah. Thanks for the kind introduction. So the title of my talk is Prethermalization in a dissipative dipolar system. So I arrange the talk in the following order. At first, I will provide a brief overview on what is thermalization and what is prethermalization. Then I will discuss how periodically driven dissipative systems or the periodically driven dipolar systems that can be used for experimental demonstration for such phases. Then I will provide a theoretical model for prethermalization. Then I will summarize. And if I have some time left, I will discuss how such prethermal phases that are connected to the time crystalline phase. So let's start. So here, a system that is coupled with the baths with a coupling constant G. And now, how does such a system thermalize? So thermalization occurs due to interaction with that baths. And in such process, a complete loss of the initial memory occurs in the system. That means if it has in any kind of initial coherence or entanglement, that will generally die out at the equilibrium. That's why preserving coherence and the entanglement that are the major challenges in quantum computation and information processing. So to tackle this problem, people introduce the concept of the prethermalization. So what is prethermalization? Prethermalization signifies a partial loss of the initial memory of a quantum system when it's connected to a bath. So you can see that I just take this plot from this paper by Peng et al., Nature 2021. Here, observable A as a function of t is plotted as a plotted in the x-axis. There is a time. You can see that there is an initial decay, and it reaches a plateau or nearly a constant phase in this regime, and there is a very slow decay, and finally it will thermalize. That means in this regime, only partial memory is lost and partial memory is still kept. So why this thing happen? Because the dynamics is constrained by several conserved quantities or the integrals of motion in this phase. So it is essentially a non-equilibrium phase, and those kind of phase has enormous application in quantum information, because still it has partial memory that show in quantum storage device and in quantum state manipulation, it has several uses. So that's why periodically driven dissipative system, they are used as an ideal test bed for demonstrating such novel phases. Here I am using some snapshot from recent articles. At first, Peng et al., they have demonstrated the experimental verification of Floquet prethermalization in a dipolar coupled 19F spins. Similarly, Beatrice, they also find the existence of the Floquet prethermalization in 13C dipolar solids in diamond. And also similarly, Tang et al., they found in dipolar quantum cradle. Among them, I am interested in the work by Beatrice et al. What they did, they have taken a dipolar ensemble of 13C diamond, and initially they are randomly oriented. So what they did, they optically pumped NB center to hyperpolarize the 13C nuclei. Now, after hyperpolarizing, initially they are in Z direction. Now, if you apply a pi/2 pulse in Y direction, that means they are oriented in the X direction. Now, a chain of spin locking pulse is applied. So here the spin locking pulse is a theta pulse. So what is a spin locking pulse? Spin locking pulse means a resonant periodic drive that is applied along X direction. So what are the outcome? You see that when there is no such pulse, the relaxation time is very fast. So for a such higher decay rate, so that time, like the green plot, they have very low relaxation time. But when they have applied such spin locking pulse, that reaction time become larger. And not only that, it has several phases. Like initially there is a transient phase, followed by a long-lived prethermal plateau, and then it will finally thermalize. So our plan is to, as this kind of systems are very weakly coupled with the environment, So we want to provide a dynamical theory from the open quantum system perspective. So here, a pictorial depiction of an open quantum system is provided. So a system S that is coupled with baths, some Hamiltonian H acting on the system. And the dynamical equation is governed by d dot t equal to L rho. L is the Liouvillean and rho s is the system density matrix. So as the system is coupled with baths, then that means you have a non-unitary process. So L should be non-Hermitian matrix, but whose real part of the eigenvalue, they are non-positive. Among them, if its eigenvalue is negative, that means you see, like if L's eigenvalue is negative, that means it is a decaying mode. And corresponding lifetime of the mode is defined by 1 by mod of alpha. Here alpha is the eigenvalue. Similarly, if L is the eigenvalue of L is 0, that means d dot t equal to 0. So it signifies the steady state. So for more clarity, I am providing analysis of the eigenspectrum of the Liouvillean. You can see that this is the eigenspectrum. Here several red circles, they are all the decaying mode because of the negative real eigenvalue. Among them, and also the green circle, it is the lowest decaying mode, and the blue circle, that is the steady state because its eigenvalue is 0. So the eigenmode corresponding the blue state, that shows the notion of thermal equilibrium. And when prethermalization occurs, when the green circle is very close to blue circle, that means the lifetime of the eigenmodes corresponding to the green circle, that will increase sufficiently. And when such condition arises, like the Albert et al. In 2014, they have shown that when there exist several conserved quantities or the integrals of motion in this non-equilibrium phase, then such kind of scenario occurs. And before more mathematical formulation, I want to provide another thing, that like the concept of the Floquet heating and its correspondence in OQS. So for isolated quantum system, a dissipation can occur from the Floquet drive, so which is also known as Floquet heating. So when Floquet heating is exponentially slow, that actually leads to Floquet prethermalization. So how they can model Floquet prethermalization? So suppose HS is omega 1 O cos omega t. So O is the operator. So Floquet heating in each cycle can be calculated from the second order contribution of the O and the multiplied by the Dirac delta function. So you see, so it is a second order phenomena. Now, if you use Born-Markov master equation, such second order dissipative effect cannot be explained from the drive, because the drive only arises in the first order. That's why we need another formulation, or that's why we are using fluctuation-regulated quantum master equation, that is proven as a better candidate for this purpose. So I am also providing an introduction to the fluctuation-regulated quantum master equation. So here you can see that this is the evolution of the system that is shown in red lines, and the bath fluctuation they have shown in blue line. So, and the fluctuation correlation timescale is defined as tau c. So what is it? If any kind of coherence is in the baths, it will be vanished within timescale tau c. So in this timescale separation, you can see that the system timescale ts is much slower than tau c. That's why as we are interested in the non-equilibrium phase of the system, that's why we are choosing the timescale delta t such that it is larger than tau c, but it should be less than ts. And when you have this kind of timescale separation, and the acting Hamiltonian that is obtained by HST is the drive, like sigma 1 omega 1 sigma x cos omega t, and the systems, each and individual atoms, they are coupled through dipolar interaction, and system path weak coupling that can be modeled using Jens-Cummings Hamiltonian. And when you have those kind of Hamiltonian and timescale separation, so propagator must be constructed in such a way it should be finite in fluctuation, but it should be infinitesimal for the system. So if you use this dynamical equation, or sorry, the propagator, you will end up with this equation. Like this is the left hand side is the change of the density matrix in as a function of time, and the first order term that is coming from drive and dipole, and the second order term, all the terms like drive, dipole, and system path coupling, they have those contributions. So if you compare this equation with the Born-Markov master equation, 2-3 interesting features will be there. Like there is a presence of exponential kernel, and along with it, when you have Born-Markov master equation, you can only access system and drive to only the first order. But when you have FRQME, they can contribute in the second order. So if you arrange this term in their strength, so this equation can be further written in this order. So here d secular is the strongest part. It is coming from the time independent part of drive and dipole. Similarly, the time dependent part, they are providing very slow decay. That's why they are, this is the middle term, they are coming from that their time dependent part. And finally, as we have to model that particular experiment, that means system path coupling is very slow. So this is the slowest component that is coming from HSL or the system path coupling. Now what we do, we just choose the initial state to be up, and also the density matrix can be written in the following order, like mij sigma I dot sigma j, and we just simulate the dynamical equation. Why I am plotting mzz not mx, because Beatrice et al, they are showing the plot for mx. I will clarify it in the upcoming slide. But whatever, if you plot mzz, you can see that there exists several, before the system goes to thermalized state, there are several dynamical phases. So initially there is a transient that is followed by first prethermal plateau. Then the first prethermal plateau will further decay to the second plateau, and finally there exists the unconstant thermalization. So now, like, we will analyze by term. Let's see. So that's why I am adding the strongest term at first. So let's consider the white part of the diagram. So you see that the strongest part, that means d secular OS, that is coming from first order and the second order contribution from the secular part of the drive and dipole. So the first order term, so it is a unitary process, so you are getting some oscillations. But as you have those kind of second order term, that means there exists a decay. But it decays to some quasi-conserved value. Why some quasi-conserved value? Because the dynamics is in that particular phase is governed by or constrained by several quasi-conserved quantity. Among them, the first one, you can see, so we'll define this as a prethermal order, and it is a linear combination of mx and mzz. That means if you start with mx, you can also get same features. Not only that, we have another conserved quantity here. If you add 2 plus 3, that means mxx plus myy plus mzz, we will define it to be the dipolar order. And this particular decay rate is defined as tau c. So in this phase, both prethermal order and the dipolar order, they are conserved. Now, if we add the non-secular term, so you can see that, like, when you add the non-secular term, like, let's consider the white part, it will further decay and reach to a second plateau. Second plateau means it should have another conserved quantity, and this is the dipolar order, and this rate is a Lorentzian in tau c. So you see that, like, in this phase, the prethermal order is broken, but still the dipolar order is preserved. So recently, Peng et al, experimentally in 19F dipolar solids, they have shown that when the prethermal order is broken, but still in their system, they have the very slow thermalization because the dipolar order is still preserved. So this analysis is experimentally backed by this experiment. Now finally, we have only last term left, that is a system path coupling. So as no such conserved quantity exists, that means it will further decay, and it decays to the thermal state, and the decay rate is proportional to omega c square tau c. Now, as I mentioned earlier, that can be analyzed using the eigenspectrum of the Liouvillean. So you see that for a two-spin system, L has 16 eigenvalues. So at first, let's consider the like the outer plot, not consider the inside plot. So you see that there are total 13 eigenvalues. Among them, 12 eigenvalues will decay in a relatively shorter time. Now, if you focus the eigenvalue at the center, and if you more zoom, that can be split into another 4 eigenvalue. So that means that three eigenvalue, they have larger lifetime because they are very close to 0. So among them, the first two, they are responsible for the first prethermalization. The third one, that is responsible for the second prethermalization. And you see that in the inset, in the real value 0, there exists one eigenvalue, and that gives the notion of thermalization. And for such process, the dark state analysis is necessary, because you see that the dark state are those kind of pure state that are not evolved under L. So those kind of state can be constructed from those quasi-conserved quantity, because that observable or the expectation value of the observable won't evolve under this Liouvillean. So that's why their eigenvectors, they can be used as a dark state. When you have a prethermalization, that means the secular part of the drive and the dipole, all the 4 eigenstate, they're acting as a dark state as they won't evolve. Similarly, when you have a constant thermalization among the 4 state, the 3 will decay, and only we left with single state that is acting as a dark state. And finally, when you have an unconstant thermalization, there exists no dark state. as there is this no concept or the conserved quantity. So such kind of states are necessary for quantum information, because you see, like dipolar interaction or the drive, they have the information of the entanglement and the coherence, like single state, that is a maximally entangled belt antisymmetric state. So, and those states have a very large, those states will decay at very larger time. That means coherence and the entanglement can be preserved using those kind of states. And finally, so before going to the slide, I will go back to this slide. You see, like there are total 3 time scale, like T3, T alpha, and T1. So T1 is a time scale for the thermalization. So this is some kind of time scale we can't avoid. So we are left with T3 and T alpha. So T3 is the rate for reaching the first prethermal plateau. It is proportional to tau c, and the 1 by T alpha is the rate for reaching second prethermal plateau. It's some Lorentzian. So you see that initially when you start the dynamics, it will reach first prethermal plateau, then it will further decay to second prethermal plateau. But when omega naught tau c less than 1, that means two decays are nearly same. That means system directly goes to the second prethermal plateau. There is no notion for the first prethermal plateau. So that's why omega naught tau c tends to 1 is a critical value beyond which, or like below which, there is no first prethermal plateau. Such limit was previously reported by Bloembergen. It's a very old work in 1948. What their group shown, like for liquids, omega naught tau c less than 1, that means that regime, and for solids, omega naught tau c greater than 1. So all those experiments which I am using in my slides, they are using solid state NMR. So why they are not using liquid state NMR? So that can be explained from this diagram. So when omega naught tau c greater than 1, that means solid, they are in this regime. So it is a finite lifetime for the first prethermal plateau. That's why they are using this limit. So I want to summarize the first part of the work. Like definitely a theoretical prescription for the prethermalization is provided, and those analytical results that are in agreement with the recent experiment using the spin locking in NMR, the Beatrice et al., their recent work. And not only that, there exist more than one quasi-conserved quantities with different decays. That's why we have two plateaus, which also recently reported in a defined system kick dipolar model by Peng et al. And there exists a critical limit beyond which such prethermal plateau doesn't exist. And we also said that so that such states have several applications in quantum storage device. So this is the work. It was published in this year February. Now I have, I think, some time left, so I'm going to the second and very small part. So how it is connected toward the discrete time crystalline phase. So what is a space crystal? So I'm using those concepts from our solid state book, Ascot Marmin. So we are considering a time crystalline potential where here periodic potential is given here, and the plot is UR versus R. Now for the electron in this potential, and we want to plot E versus K diagram. Suppose electron is a free particle and E is proportional to K square. So it is a continuous plot. But when there exists some kind of periodic potential, you see that, so it is not a continuous thing, a discrete nature arises. That means space crystalline is formed when the continuous space transition symmetry is spontaneously broken to a discrete symmetry, and the discreteness that can be defined using the reciprocal lattice vector. So motivated by those concepts, Wilczek in 2012 proposed that that role of the time and the space can be interchanged such that the continuous time transition symmetry can be spontaneously broken. But such realization of continuous time crystal is under big question, because Bruno and Watanabe in 2013 and 2015, they have proposed a no-go theorem. So you can visualize the theorem in this way. Suppose you are applying a time periodic perturbation, and suppose the system is reaching to the thermal equilibrium state, then what do you expect? A thermal equilibrium state should be always a time independent state. So that particular continuous time transition symmetry can't be broken. But the research won't be stopped here. People are more thinking about it and came up with the concept of discrete time crystal, which was proposed by Else in 2016. What he proposed, suppose you are applying a Hamiltonian H with a periodicity T, and you are plotting or you are observing some observable of the system. Now suppose the system spontaneously switched to a periodic motion with a different period than the period of driving. That means the period of the observable is multiple integer with the period of the Hamiltonian. So when such condition satisfies, that means there exists a discrete time crystalline phase in the system. So obviously it should be a non-equilibrium dynamical phase. And when some such concept is came to the all the physics pupils, they are thinking about experimental demonstration. That's why NMR provides a useful platform for trapped ion, NV center, NMR crystal. In all cases, I'm not going detail to the experiment, but one thing for sure you can see visualized by this picture. Suppose all those cases, some Hamiltonian is acting in the system and its periodicity is T. Now they are plotting the some Fourier spectrum of some observable. It may be some global polarizations or some transverse magnetization. All those cases, the peak is arising at 0.5. So omega equal to 0.5. That means it is 1 by omega. So it is a 2T periodicity. So for the periodicity of the Hamiltonian T, you are getting a 2T periodicity. That's why this is known as the discrete time crystalline phase in this system. I am only interested in this work by Choi et al. What they done, they are using dipolar coupled NV centers in a black diamond, and a laser is applied. Now again, like a pi by 2 pulse is given such that they are oriented in x direction, and the spin locking pulse, like what the theory I am telling you in my earlier or the first part of the talks, like how spin locking pulse is helps you to reach the prethermal phase. Now same spin locking pulse is applied for a time t1, followed by a rotation around the y-axis t2 is given, and that total time evolution that is repeated for n times, and finally they just measure the signal. Now what they get, so when you have a very small t1, that means very small time for the spin locking pulse, and a perfect pi rotation is applied. So you can see that each and every cycle it actually changes sign. That means after 2 period it is actually getting same sign. So definitely they are getting a peak at omega equal to 0.5. But when for same small t1 tau1 and some perturbation applied such that pi plus delta rotation allowed along is applied along y, so a pi delta perturbation is applied. For this case, such 2T periodicity is broken as they are getting 2 peaks instead of getting 1 peaks. So definitely it is gone. But they retrieve the signal by increasing the larger tau1 and same perturbation. That means if you increase the spin locking time, that is a larger tau1 and very smaller delta, that is a favorable condition for the DTC phase or the discrete time crystalline phase. So can we have a dynamical theory? Because we already have a theory for the spin locking. That's why. So this is the dynamical equation for the spin locking pulse, which I am describing my earlier part. Now, followed by that, a rotation like HY along Y direction is applied such that this is my dynamical equation, and that is repeated for n times. And the initial state, as after pi by 2 pulse, all the spins are oriented along x direction. That means I am choosing my initial state as the eigenstate of sigma x, that in 1 by root 2 up plus down. Now, if we and then what we do, we just depending on the cycle, we are repeating that signal. Now, if we dynamically or numerically simulate it, what we find, our numerical analysis or the numerical result, they are exactly matching with Choi and their groups get. That means smaller delta and the larger tau1, that is a favorable condition for obtaining the DTC phase. Here you see that for some smaller delta, when exactly pi pulse, we have getting a periodicity at omega equal to, yeah, here as it is like multiplied by 2 pi, that's why it is arising in pi. But when there is a rotation, that is pi plus delta, such thing is broken for larger t1, that can be retrieved. So one thing extra, like as in our theory, another parameter is tau c. So we can see that. So tau c is actually fluctuation regulated time scale or fluctuation coordinated time. It is inversely proportional to temperature. That means for a larger T1, when we are getting such kind of prethermal response, if we decrease the tau c, that means if we increase the temperature, we see that such 2T periodicity is gone. That means our time crystalline phase, that is more stable in lower temperature. So I will finish my talk in this two take home message, because you see, like, this is ongoing work. So we say that prethermalization actually helps in stabilizing the DTC phase under the smaller perturbation, and such 2T periodic response or the DTC phase, that is more robust in the lower temperature. Thank you.
Thank you, Mr. Saha, for your very nice talk. So I would request any of the participants who would like to ask a question, please unmute yourself and ask, please.
I have one question.
Yeah, sure.
Thank you for your talk.
Yeah. Yeah.
In first part of your presentation, you mentioned about quantum storage.
Yeah.
So, do you have any estimations on maximum storage time for quantum states?
Okay. So you see that in this experiment by Beatrice et al. So you see, like it is a T2 time, it is 573 second. So I mean 10 to the 2, but so it is a T2 time. But before that, you see that there is a prethermal regime that is 10 to the minus 2 to like 10 to the 0 second. So in this time, there is a plateau and the system is locked in particular state. So in that particular time, you have several states that can store information. So that is the storage time, and we can predict from this experiment. That is the time. Or similarly, in our simulation, you see that like this time. This is the time, because your system is nearly locked. And its consequence, like there are several states, they are not evolving, and those states are the information of the entanglement and the coherence. So there's the time where, as the system is not evolving, so we can think about making a storage device using this configuration, because the system, in presence of thermal environment, still the system is locked. That's the thing.
Okay. Then how about reading of information? Okay, we can store, and then we have to read. Or
Yeah, I
we
mean,
have to read.
that part, like I'm not an expert, so we are just here giving a theory, like which regime the such information can be stored. Then definitely it is a very good question. Definitely we can think about how to read those kind of like extract the information of the entanglement or coherence. That I have to check.
Thank you.
Yeah, thank you, sir.
Okay, so are there any further questions? Okay, so if there are no more questions, we would like to thank the speaker, Mr. Saptarshi Saha, for his time and